Chapter 3 National Income How It is Earned. Let's begin this chapter by asking a fundamental question. What determines the total production or output of goods and services in an economy? We'll focus on a closed economy, meaning there is no trade with the rest of the world. We'll also use a market clearing model, which assumes that all markets are competitive and adjust to balance supply and demand. Let's break this model down into three main components. The supply side. We start with the factor markets where households supply inputs like labor and capital, and firms demand them. These interactions determine factor prices like wages and rental rate, and allocate resources. The result is the determination of the economy's total output or income. The demand side, we look at what drives spending in the economy, specifically the components of aggregate demand, consumption, investment, and government spending. Each component has its own underlying behavioral model, which we'll explore in detail in Chapter 4. Equilibrium. Equilibrium occurs where aggregate demand equals aggregate supply. This condition must hold in both the goods market and the lawnmower funds market. This framework will guide our analysis of how the economy determines output and allocates resources in the long run. Let's now talk about the building blocks of production in an economy, starting with the factors of production. K stands for capital. These are tools, machines, factories, and structures used in the production of goods and services. L stands for labor. This includes both the physical and mental efforts of the workers in the economy. We represent the relationship between inputs and output with the production function. Y equals to function of K and L. This tells us how much output Y the economy can produce, given certain amounts of capital K and labor L. It's a core concept of understanding how economies turns inputs into goods and services. Returns to scale. Now suppose we scale up all inputs by the same factor Z. What happens to output? Start with Y1 equals to function K1 L1. Scale inputs K2 equals ZK1 and L2 equals ZL1. Output becomes Y2 equals to function K2 L2. There are three possible outcomes. Constant returns to scale if Y2 equals ZY1. Increasing returns to scale if Y2 is greater than ZY1. Decreasing returns to scale if Y2 is less than ZY1. Understanding the type of returns to scale helps us predict how economies respond to growth in inputs over time. Let's work through a couple examples to determine the types of returns to scale based on different production functions. Example number 1. Suppose the production function is function KL equals to the square root KL. Now scale both inputs by a factor of Z. Function ZKZL equals to the square root ZK times ZL. That equals to the square root Z square KL. That equals to Z times the square root KL. That equals to Z times the function KL. Conclusion, this function exhibits constant return to scale when Z is greater than 0. Example number 2. Suppose the production function is function KL equals K square plus L square. Now scale both inputs by a factor of Z. Function ZKZL equals to ZK overall square plus ZL overall square. That equals to z squared k squared plus z squared L squared. That equals to z squared times k squared plus L squared. That equals to z squared times function KL. Conclusion, this function exhibits increasing returns to scale when z is greater than 1. Before we go any further, let's outline the assumptions we're making in this model of the economy. Technology is fixed. We are analyzing a long-run steady-state scenario where the production technology does not change over time. The supplies of capital and labor are fixed. That is, we assume the economy has a fixed amount of productive inputs. K equals K bar, L equals L bar. Output is determined by these fixed inputs and technology. Given a production function, the total output of the economy is y equals to function of K bar, L bar, that equals to y bar. In other words, with no changes in input quantities or technology, the level of output is predetermined. In this section, we explore how the total income generated in an economy, its national income, is distributed to the factors of production. In our model, firms hire labor and capital to produce goods and services. The payments that firms make to these inputs are called factor prices. The wage is the price paid per unit of labor. It reflects how much a firm pays each worker or hour of work. The rental rate is the price paid per unit of capital. This is the cost of using machines, equipment, or buildings. These factor prices are determined in comparative markets, where firms decide how much labor and capital to hire based on how much those inputs contribute to output. This diagram shows how income flows from firms to households in the form of wages and rents, distributing national income to the owners of labor and capital. It shows how factor prices are determined in the comparative market. Factor demand, downward sloping due to diminishing marginal returns. Firms demand less as price rises. Factor supply, vertical, fixed supply in the short run. The intersection gives the equilibrium factor price, where demand equals supply. Let me introduce some key notation and explore how a comparative firm makes hiring decisions. W is nominal wage. R is nominal rental rate. P is price of output. W over P is real wage, measured in units of output. R over P is the real rental rate. Firm behavior in comparative markets is that firms are price takers. They take W, R, and P as given. The basic idea is that a firm hires each unit of labor if the cost does not exceed the benefit. That means cost equals real wage and benefit equals marginal product of labor. Firm's profit maximization is that profit equals revenue minus labor cost minus capital cost. That equals to PY minus WL minus RK. That equals to P times function of K and L minus WL minus RK. This equation forms the foundation for understanding how firms choose labor and capital to maximize profits. Now let's look at how firms decide how much labor to hire based on productivity. Firms' demand for labor. Most production functions exhibit diminishing marginal product. As you add more of a factor like labor, the additional output from each extra unit decreases. This graph illustrates the relationship between labor input L and output Y, given a fixed amount of capital K. The curve represents the production function, a function of K and L. the slope of the curve at each point corresponds to the marginal product of labor, MPL. As more units of labor are added, the MPL diminishes. This is shown by the curve becoming flatter, a clear illustration of the law of diminishing marginal returns. Marginal product of labor is the additional output produced by one more unit of labor, holding capital constant. MPL equals to a function of K and L plus 1 minus a function of K and L. In calculus form, this becomes MPL equals to dF over dL. This is the partial derivative of output with respect to labor, holding capital constant. Alternatively, using change in output and change in labor, we can approximate MPL equals to delta Y over delta L. That equals to Y2 minus Y1 divided by L2 minus L1. Understanding MPL helps us determine how much labor a profit-maximizing firm will choose to hire. Let's focus on how a profit-maximizing firm decides whether to hire an additional unit of labor. The firm compares the additional revenue from hiring one more worker to the additional cost of doing so. The change in profit from hiring one more unit of labor is delta profit equals delta revenue minus delta cost, where delta represents the change in. So delta profit equals P times MPL minus W. To maximize profit, the firm will hire labor until the point where delta profit equals 0. So P times MPL equals W. Rearranging this gives the condition MPL equals W over P. This means that the firm hires labor up to the point where the real wage equals the marginal product of labor. If MPL is greater than W over P or real wage, firm hires more. If MPL is less than W over P or real wage, firm hires less. Example, compute MPL based on the data provided. Here is how to calculate MPL. For example, when L equals 3, MPL equals 27 minus 19 divided by 3 minus 2, that equals to 8. When L equals 7, MPL equals 49 minus 45 divided by 7 minus 6, that equals to 4. This pattern continues, showing a decrease in MPL as L increases, demonstrating diminishing marginal returns. Let's apply our decision rule using a real wage of W over P equals 6. Now we evaluate whether the firm should hire more or less labor at different levels of employment. Case number 1. If L equals 3, from the table, when L equals 3, MPL equals 8. Since MPL equals 8 is greater than W over P equals 6, the additional output from hiring one more worker is greater than the cost. The firm should hire more labor. Case number 2. If L equals 7, from the table, when L equals to 7, MPL equals 4. Since MPL equals to 4 is less than W over P equals to 6, the cost of hiring exceeds the benefit from the extra output. The firm should reduce the amount of labor hired or hire less. Let's walk through these two diagrams to understand how the real wage and employment level are determined in a comparative labor market. Top graph, labor demand. This graph shows the MPL curve, which also serves as the labor demand curve for firms. The downward slope reflects diminishing marginal product of labor. As more workers are hired, the additional output each one contributes falls. The firm hires labor up to the point where MPL equals to W over P. At this point, the real wage equals the value of the marginal product of labor, and we determine the quantity of labor demanded. Bottom graph, labor market equilibrium. Now we add the labor supply, which is vertical, perfectly inelastic, and is modeled, representing a fixed amount of labor, L bar. The intersection of labor demand and labor supply curves determines the equilibrium real wage and the equilibrium quantity of labor employed, L bar. In equilibrium, the labor market clears. All available labor is employed at a wage where firms are willing to hire exactly that amount. Let's now turn our attention to the marginal product of capital. MPK represents the extra amount of output a firm can generate when it adds more unit of capital, holding the amount of labor constant. Formally, we define the marginal product of capital as MPK equals function of K plus 1 and L minus function of K and L. This is the change in output where we increase capital by 1 unit, keeping labor fixed. In calculus terms, this becomes the partial derivative of the production function F with respect to capital K. MPK equals dF over dK. Or in discrete terms, MPK equals to delta Y over delta K. That equals to Y2 minus Y1 divided by K2 minus K1. Understanding MPK is critical because it helps us explain how firms decide how much capital to use and how much capital contributes to overall production. Firm's capital hiring decision. A profit-maximizing firm will rent capital if the extra revenue from that capital exceeds its cost. The change in profit from renting 1 more unit of capital is delta profit equals delta revenue minus delta cost. That equals to P times MPK minus R. The firm rents capital until this profit change is 0. So P times MPK equals R. Then MPK equals R over P. This condition tells us the firm's demand for capital, higher capital up to the point where the real rental rate equals the marginal product of capital. Here we explore how income is distributed to the factors of production in a competitive economy. The key idea is that if all firms are competitive and profit maximizing, then each factor of production is paid according to its marginal product. W over P equals MPL and R over P equals MPK. Total payments to factors. Total real wages paid to labor or labor income equals MPL times L, and total real return to capital or capital income equals MPK times K. National income decomposition. National income Y is the combination of labor income, capital income, and economic profit. So economic profit equals Y minus MPL times L minus MPK times K. If the production function exhibits constant returns to scale, then economic profit is 0. Then Y bar equals MPL times L bar plus MPK times K bar. This is consistent with Euler's theorem. Function L and K equals MPL times L plus MPK times K. Now let's look at one of the most commonly used functional forms in macroeconomics, the Cobb-Douglas production function. The Cobb-Douglas production function is written as Y equals A, K, take the exponent alpha, L takes the exponent 1 minus alpha, where Y is output, K is capital, L is labor, A is total factor productivity or technology, and alpha is a parameter between 0 and 1. Factor shares of income. Alpha is the share of output paid to capital or owners of capital. 1 minus alpha is the share of output paid to labor or workers. This implies capital income is MPK times K equals alpha times Y. Labor income is MPL times L equals 1 minus alpha overall times Y. Now let's take a closer look at the expressions for the marginal products of capital and labor derived from a Cobb-Douglas production function. Marginal product of capital, MPK, is the partial derivative of y with respect to capital K, and it equals dy over dk that equals to alpha ak take the exponent alpha minus 1, L take the exponent 1 minus alpha that equals to alpha times y over k. This tells us how much additional output is produced when we increase capital by 1 unit, holding labor fixed. Marginal product of labor, MPL, is the partial derivative of y with respect to labor L, and it equals dy over dl that equals to 1 minus alpha overall times ak take the exponent alpha, L take the exponent negative alpha that equals to 1 minus alpha times y over L. This gives us the additional output from using 1 more unit of labor, holding capital constant. Now let's think about how these marginal products respond to changes in inputs and technology. As capital K increases, MPL increases, but MPK decreases. More capital boosts labor productivity, but each additional unit of capital adds less output. This is diminishing marginal returns. As labor L increases, MPL decreases, but MPK increases. More labor reduces its marginal product, but increases the productivity of capital. And as technology A improves, MPL increases and MPK also increases. Technological progress raises the productivity of both labor and capital. So changes in factor quantities in technology directly impact the marginal productivity of inputs, and this plays a key role in how firms decide how much of each factor to employ. Up to this time, let's go through a couple of practice problems to reinforce our understanding of marginal products, input prices, and income distribution in a comparative economy. Question number 1. A firm manager observes the following. MPL is 5 units per hour, MPK is 40 units per machine, wage is $20 per hour, the rental price of capital is $120 per machine, and the price of output is $5 per unit. The question asks, to maximize profit, should the manager hire more or less labor and rent more or less capital? Here how to solve this question. Step 1. Calculate the real input costs. That is, real wage equals W over P equals 20 divided by 5 equals 4. And real rental price equals R over P equals 120 divided by 5 equals 24. Step 2. Compare to marginal products. MPL equals to 5 is greater than W over P equals 4. So hire more labor. MPK equals 40 is greater than R over P equals 24. So rent more capital. The answer is A. Hire more labor and rent more capital. Question number 2. Suppose the production function is Cobb-Douglas. That is, y equals 10k takes the exponent 1/3, L takes the exponent 2/3. The question asks, if the stock of capital doubles, what happens to the share of income paid to capital? From the Cobb-Douglas production function, the income shares are constant. Capital share is 1/3 and labor share is 2/3. Suppose capital doubles, so y equals to 10, 2k overall, take the exponent 1/3, L take the exponent of 2/3. that equals to 10 times 2 take the exponent 1/3 times k take the exponent 1/3 times L take the exponent 2/3. We can see that alpha equals to 1/3. That is, the capital share stay the same. Why? In the Cobb-Douglas production function, factor shares alpha and 1 minus alpha are constant, regardless of input quantities. So the answer is D, stay the same. Now let's walk through 2 examples to determine whether a production function exhibits constant, decreasing, or increasing returns to scale. Example 1. Let's start with the function KL equals k squared over L. To test for returns to scale, we scale both inputs by a factor z. So function zk/zl equals zk over L squared over zl equals to z times k squared over L equals to z times function KL. So when we scale both inputs by z, output increases by the same factor z. The conclusion is this function has constant returns to scale. Example 2. Now consider function KL equals k plus L. Scale both inputs by z, so function zk/zl equals zk plus zl equals to z times k plus L equals z times function KL. Again, output increases exactly by z. The conclusion is this function also exhibits constant returns to scale. Let's determine which of the following production functions exhibit diminishing marginal returns to labor. Example 1. Function KL equals 2k plus 15L. Compute MPL, that is partial derivative of f with respect to labor, equals to 15. Since MPL is constant, it does not diminish. The conclusion is not diminishing marginal returns to labor. Example 2. Function KL equals to the square root of KL, or we can write it as k take the exponent 1/2 times L take the exponent 1/2. Compute MPL, that is the partial derivative of f with respect to labor, that equals to 1/2 times k take the exponent 1/2 times L take the exponent negative 1/2, that equals to 1/2 times k take the exponent 1/2 divided by L take the exponent of 1/2. As L increases, MPL decreases. The conclusion is diminishing marginal returns to labor. Example 3. Function KL equals 2 times the square root of k plus 15 times the square root of L. Compute MPL, that is partial derivative of f with respect to labor, equals to 15 over 2 times the square root of L. As L increases, MPL decreases. The conclusion is diminishing marginal returns to labor. In sum, this chapter lays the foundation for understanding how national income is both generated and distributed in a closed economy. By analyzing how firms demand labor and capital and how these factors are compensated according to their marginal productivity, we uncover the role of market forces in shaping income allocation. In the end, production and income are inseparable. What an economy produces ultimately determines what it earns.